All right, hello. So I want to give some hints on two of your Smartwork problems here. The first one's going to be question 11, where we have some mass of water that we're adding to an iron skillet. The skillet is very hot, presumably, and will boil all of that water. What will be the temperature change of that skillet? And we are given the mass, and we're also given the heat capacity in the problem. So I don't want to go through this uh, and take away all the fun, fun quote. Uh, but whenever we're looking at these problems, we have that conservation of energy. So I know that all of our temperatures, all of our, Qs, our heat exchanges are going to balance out. They're going to add up to zero. In this case, we have that hot metal skillet. Oh, there it goes. Now it's updating. We drip that water on there and it's going to boil. So we know that increasing the temperature of water, it's going to have to go from, uh, if we just write that down, our water's going to have to go from its initial temperature to the boiling point, and then it will boil. Call that specific gas steam, right? It's not going to change temperature after that. We do say at 100 degrees C, it escapes. And that makes sense because if it's 100 degrees C, it's going to fly out of our pan and quickly cool off and recondense somewhere else in our room. Unless your room is not saturated, if it's not humid in there. So, how do we approach this? We want to think about this. We want to think about how do we describe these heat changes? How do we describe the temperature change of the iron? So, this pan, assuming we're not adding any heat to it, which, if this is on a stove, that's probably not true. But the pan starts at some initial temperature and it's going to transfer all of this energy required to boil the water. So all of the energy going into boiling the water comes from the pan. So this pan is going to give that some kind of temperature change. We don't know what that is, but we're going to find it. So here we have two, I'm going to do a different color. We have two different functions going on, right? And down here, we have a third one. So we can describe each of these with a Q. This is a delta T, right? So we're going to have the M, C, delta T. And when we write these, we want to be very careful that we're thinking this is the mass of water. This is the specific heat of water. This is going to be the delta T of water. We have this one. So we didn't quite make it here in lecture, but we did gloss over it very quickly. And it's at the end of our lecture slide deck. But we can describe the energy of a phase change with either Q equals N, delta H, in this case boiling, that will be vaporization, right? We could also use M delta H, vaporization. That's just going to depend, is this defined in kilojoules per mole or kilojoules per gram? And one thing you'll notice about all of our Q equations is all of our Q equations, our heat transfer equations, connect energy, units of joules, to some quantity, either moles or mass times temperature changes, something like that, something that's going on. And then lastly, our iron, that's also going to be a temperature change, but that's going to be a temperature change of our iron. And we are fortunate that we are just asked to solve for this guy, right? So brandishing new color, not super high contrast, but we'll take it. So, what else do we know? What else do we need to know? We're told the mass of water in the equation. We are told the final and initial temperatures of the water in this situation. We, again, we know the mass of water. This one, I don't think it's given to us in the problem, right? The, yeah, so the problem's a little mean there. Does not tell you the delta H vaporization. That is in the lecture slides. That is a constant. So, right, it's probably dependent on pressure, but we assume all these happen at atmospheric pressure. So that's a constant. We can look that up. So we have that. CW is a constant. We are told the mass of the skillet. We're told this is a molar heat capacity in our problem. So this is given to us as joules per mole. Kelvin or Celsius. Why don't we just make it Celsius? So we do have to be careful that we account for that. We can't just plug mass in here. We have to do some kind of conversion. And then we can find delta T. So we know everything else. We know that, why don't we add QFE, QW, Q, we'll just call it QFAP. And one thing we should be careful of, which we're fortunate in this case, is the directionality of this. And by this, I mean of this. So vaporization is endothermic. It will have a positive delta H. If we were going the other way, we would have to remember to negate that. So we have three Qs here, right? Q1 or Q2, Q3. They add up to 0. Unfortunately, I don't think I can give you any more than that without like really spoiling it. And then I want to look at homework 12. All right, so this is question 12. I just scribbled it in there quickly. And what this question is asking, how much energy is released when a mass of water goes from solid ice, so below 0 degrees Celsius, to something, to gaseous steam, something above 100 degrees Celsius. And we're not stopping at these, we're going past them. So this is not greater than or equal to or whatever. So this one, we almost got to phase changes. But when we're looking at a system, let me not scroll it up yet. We want to think about what happens to it, right? So we have this ice cube. Let's just say, for argument's sake, that it starts at negative 12 Celsius. As we add heat to it, what's going to happen is it's going to increase in temperature until it reaches its melting point, at which point it's going to melt. So, change in temperature, melt. Now we have a puddle of water. And that's going to, and that puddle of water starts at 0, right? Because it's finished a phase change. It's going to undergo a temperature change until it starts to boil. At 100 degrees C. And then it's going to be a gas. This is my abstract drawing of steam vapor. Isn't that exciting? And let's just say it ends at, I don't know, 114 Celsius. And what'll that be? That'll be uh, mixed phase. So I guess I need to draw this twice because this is it boiling. So when it boils, nope, we want to duplicate. Boop. We're going to have to move all of this over. Here we go. Beautiful. And we're going to move that temperature over. There we go. Something felt off. I was missing the same temperature twice in there. All right. So that will be the journey of our water. Another way we can think about this is, and we would have loved to talk about this, right? So we have delta H and temperature. So if we're watching that ice cube melt and turn into gaseous steam, what we're going to observe is that temperature is going to increase until we hit the melting point, which would be 0 degrees C. We're going to see it level off. So even though we're adding heat into the system, we're not changing the temperature. That's because we're undergoing a phase change. So we're taking that ice and we're melting it. And that requires breaking the potential energy bonds between molecules. So in water, you have all those hydrogen bonds, all those strong intermolecular forces. And in order to change ice into water, you have to break them. As we said, breaking bonds takes energy. And what's interesting here is that the average kinetic energy of the molecules doesn't change during this. So whether or not they're stuck together in a giant clump that moves at one speed or they break off and move as individuals, they're all moving at the same average speed, the same root mean square. We'll talk about that later. Maybe. I don't know if we'll talk about root mean squares. So here we spend all this energy. We're breaking it up. Once we have liquid and only liquid, all the ice is gone. We see that temperature increase again. And if I drew this to scale, I think actually the specific heat of water is much higher than ice. So we would see that temperature change go up more slowly. The same rate of energy input here would result in slower change just because the specific heat of water is higher than ice. And that's important to know, that the specific heat depends on the phase. Then we get over to our boiling. So we have to put energy in there. Notice that I'm putting in a lot of energy. So when I go from a solid to a liquid, I only have to break a couple intermolecular forces, a couple of those bonds, to kind of shake my crystal down enough to make a liquidy blob. So I still have lots of intermolecular forces, but no coherent structure. In order to make a gas, you have to break every single intermolecular bond so that those particles can go whizzing off from their friends. So that is a much more expensive process. So it takes more energy typically to boil. If you look at heat of fusions versus heat of vaporization, heat of vaporizations are, I want to say always, but the scientist in me is like, So we're going to say in general, they're much higher. And then the same thing, once you have managed to break all that liquid, you are going to get a rapid temperature increase. And it just so happens that the specific heat of ice and steam is actually very similar. They are about half as much as the specific heat of water, but otherwise quite close. And we'll move this swiggle over there. We'll extend our axes a little, and we'll move our T. So that's kind of the theory of what happens here. And this one, we don't need energy conservation at all. We're just asked how much energy happens from this process. Energy conservation would be if I asked, okay, I did this by putting the water on, I don't know, a really hot skillet, and the skillet ended at, or I guess that maybe you'd want to know what temperature the skillet is at this point. A strange question, but one that maybe you could do. so we're going to go back to, you can use either of these. The diagram down here is a little more concise. Why don't we put some color in it? Purple. Purple seems good. So we have a delta T, we have a delta H fusion going on here. We have a delta T, we have a delta H vape going on here, and we have a delta T. Notice that my deltas kind of look like circles, and that's because they have rounded triangular corners. All right. So all we have to do is add up each of these energy changes, right? Because the whole time we're adding in energy. I didn't label it, but on here, this is going to be 100 degrees Celsius, right? That boiling point. We stay at the boiling point. This is also the way people calibrate thermometers. So you put thermometer in an ice bath. That ice bath, assuming it's pure water, will be 0 degrees Celsius. You can find out what 0 is on your thermometer or what your thermometer thinks 0 is. And the same for boiling. You put your thermometer in boiling water and see what the temperature is there. Both of those are pressure dependent, especially that latter one, but whatever. All right, so we just need to find out the Q. Let's go with purple. So we have the Q of our ice undergoing a delta T. We have the Q of our ice undergoing a phase change, melting. Now it becomes water. So we have the Q of water undergoing a delta T. We have the water boiling to become a gas. And then I never have enough space for these, right? That's the golden rule. There's never enough space to write this down. We have the Q of steam undergoing a delta T. So, and once we add all of those up, we'll get our answer. So both of these, I like these problems because they have a couple steps. So this one has 3 steps. This one has 5 steps. Individually, I think the steps are doable. But again, a lot of this is just slowing down, thinking about what's going to happen, and then how do I ascribe that to kind of the quantitative side of what we've learned. So that's it. These are my my tips for this homework. This was an 18-minute video. Smartwork does think each of these problems will take you about 20 minutes. Let's go back here. Okay, so thanks. Question 11 will take you 12 minutes, and question 12 will take you 19 minutes. So, long explanation for those. I hope that's enough without over spoiling it, and I will see you guys in whatever our next video is. And if you use this as a sleep aid, that's also okay.